and operates that treatment plant to produce high quality water for pumping to Singapore. It's a pretty unique situation. The treatment plant is called the Johor River Waterworks, and it's at a little town called Kota Tinggi, up at, sorry, I'll come back to that in a minute, which is about 30 or 40 kilometers north of Johor Bahru. And it's treated there using high state-of-the-art treatment process and then pumped to Singapore. Now the Johor River is tidal in that the sea comes up, makes its way up the river during high tides, and the treatment plant up there is not able to extract salinity from water, and therefore it's important that this salinity does not travel past the intake to this treatment plant. This has happened over the years, and sometime in the 1990s, Singapore built this thing called the Lingui Dam, Lingui Reservoir, and this is a you may have heard of that in the news, and quite often it shows you that the level in the Lingui Reservoir has fallen, and the impression is given that that's where we get our water from. But actually, the Lingui Reservoir is a controlling reservoir to control the salinity ingress up the river so that it doesn't reach the intake of the treatment plant. One of the things that's happened over the relationship, the water supply from Malaysia has always been a political hot potato over the years, but what it's become recently is being affected by climate change, and therefore the level in this reservoir has depleted, and I don't think it's too bad at the moment, but it's gone down significantly on various occasions, and therefore its ability to regulate the salinity in the Johor River has been badly affected, and therefore the treatment plant at Johor River Waterworks has had to shut down on quite a few occasions, and I think we'll see more of that as we go forward. Now, this treatment plant is actually the biggest treatment plant that PUB owns. It's 250 million gallons per day, and it pulls from this river, which is called the Johor River. And I think you'll see here in my picture that a few years ago, the Malaysian government, working with the Singapore government, decided to barrage this river. And you can see the barrage there. And you can see what the effect of the barrage has been on the water quality on either side of the barrage. There's a lot of silt and sand and other things that are to the left of the barrage, and that's what feeds the Johor River Waterworks. The other issue is that because Singapore does not own the catchment, then this catchment is entirely unprotected, unlike the catchments in Singapore. I'll show that in the next picture. Yes, so Singapore owns and operates this reservoir in this treatment plant in a foreign country, and this catchment in Malaysia feeds this treatment plant, and so PUB has got no control over it whatsoever. The quality of what happens in the catchment, and depends on a lot of cooperation with the Malaysian authorities to make sure that does not affect the operation of the Johor River Waterworks. This state of Johor, as you know, is heavily planted with palm oil, and the use of pesticides and other chemicals is a real issue for the treatment plant. As a result of that, the Johor River Waterworks includes ozonation and activated carbon, which helps to deal with the range of pesticides and contaminants that arrive at the plant. So quite a unique situation. Now, just before we go on to the next slide, this agreement to provide water from the Johor River was set up by the British government before they departed Singapore in the 1960s. And the agreement then was that Malaysia would allow Singapore to abstract 1,000 gallons of water from the Johor River for the princely sum of 3 Malaysian cents. And that number has never changed over the years, not even through indexation or anything else. And it's been a bone of contention. And the other thing that it's done is to make the water supply from the Johor River and treated in Johor River Waterworks very cheap. In fact, it's by far the cheapest um, of the 4 national taps. And as a result, it tends to be treated as the base load. And that causes us, Colin, myself, lots of problems when we're designing treatment plants in Singapore. So the water produced from Johor River Waterworks is treated and pumped to Singapore. And if you ever go across the causeway, you'll see these great water pipes that have been there for a long time. And this brings high quality drinking water across the border. Once it gets across the border, it gets distributed through a whole web of distribution pipes. There are a number of service reservoirs, all of which are interconnected, and the Johor River Waterworks and the other treatment plants around the island can deliver into these reservoirs, and from there it gravitates into supply more generally, but it's a complex web. So then we have water which is produced, which is captured from the catchment. And this is a map of Singapore with the catchment. And what's pretty unique about it is that right now, 2/3 of the island is a catchment. Every opportunity that PUB gets to collect water and retain it for treatment is exploited. With the backdrop, of course, that we have a serious flooding problem. So what you'll find is that a lot of the coastal reservoirs have been provided with gates and dams. And if you drive along Kranji or Seletar reservoirs, and of course the Marina barrage is the most recent example of that, where all of the sea intakes are basically turned into fresh water bodies rather than seawater bodies, and that will happen naturally with time once you have put the barrage across them. Okay, so the Marina barrage is the great example of this, which helps form something called the reservoir in the city. And the benefits of that are we have another reservoir. It also prevents flooding because it prevents the tide from coming in and raising the level in the Singapore River. And of course, it operates as a lifestyle attraction, as you're all very much aware. So that's been in operation now for, I don't know, 15 years or so. And what's interesting is that, and people might not know this, but in this building that you see at the end of the barrage is one of the biggest pumping stations in the world. And its job is to lift, in the event of a 1 in 100-year storm and a high tide on the other side of this barrage, is to lift the river flows up over the barrage and out the other side. And those pumps are something else if you get a chance to go and see them. Okay. Let me see if I can get this to work. Okay. So let's talk about drinking water plants or waterworks at the moment on the island. So these waterworks draw from the reservoirs, and there are 5 waterworks, fairly major waterworks, over at the west at Choa Chu Kang, in the middle here at Chestnut Avenue, and then at Woodley Waterworks and then in the north there's another one at Lower Seletar and then one at Bedok. So these are all strategically located to draw water from the reservoirs. As well as that, we have some desalination plants, and on the left of this, and so I've used the RO membrane symbol here to represent these. These are huge desalination plants, all of which use sophisticated treatment processes to desalinate the sea and to pump it into that network that I showed you earlier on. On the west of Singapore, there are actually 3 desalination plants with a total of a very large installed capacity. On Jurong Island at the moment, we are currently designing the 5th desal plant, and of course, very recently, and you'll seen this in the news, the amazing Marina East desalination plant was commissioned, and you'll see that as the latest addition to the right in the middle of the parkway down there. So it's really worth a visit if you can go there. And this treatment plant, for example, has got a green roof where people can access for leisure, and all of the workings are in 2 basements. So it's a very huge undertaking to build this thing. Now, the interesting thing about this plant is that it has an intake on either side of the barrage, and so it can treat seawater, or it can treat the water which is in the Singapore River on the other side of the barrage, and that is commonly known as brackish water. And so the treatment of brackish water uses a lot less energy than the treatment of seawater, and so this is called a variable salinity plant, because of that reason. And so it allows PB to minimize the cost of production. So in terms of the ability to produce drinking water, it's a mix between the drinking water plants, which has got an installed capacity of 345 million gallons per day. Now the average consumption here in Singapore is about just over 300 million gallons per day. So even the Waterworks in Singapore are able to provide that irrespective of Johor River, but there's not enough stored capacity in the reservoirs to sustain that. And therefore desalination is required because the sea is always there. And right now we have 160 million gallons per day of installed capacity of desalination plants. On the left here, this picture is our Tuas Desalination Plant 3, as we call it, which was opened about 18 months ago, and that's 30 million gallons per day. On either side of this plant, there are 2 other seawater RO plants. One of them, I think you'll have seen the hullabaloo in the press about the High Flux organization and their part in these 2 treatment plants. One of them has gone back into PB ownership, and the other one is still owned by the original owner. Okay, so seawater desalination plants, we have a high installed capacity of 160 million gallons per day. By 2021, that will rise by another 30 million gallons per day. And together with the Waterworks, we have a huge installed capacity, given that the Johor River Waterworks is by far the cheapest source of water and the base load. And when I said earlier that causes Colin and myself problems, when we design plants in Singapore, they have to be designed for a large output, but turned down to the minimum because of the cheapness of the Johor River supply. Of course, the other issue is that desalinating seawater is by far the most expensive thing to do. And the reason for that is because of the energy associated with desalination and through reverse osmosis and the osmotic, the process of osmosis. And so currently that stands at 3.5 or thereabouts kilowatt hours per cubic meter of drinking water. And that is probably 20 times more expensive than producing it in a drinking water plant. And to put NEWater into comparison here, the specific energy consumption for NEWater compared to this 3.5 is 0.75 kilowatt hours per cubic meter. And therefore, it's far cheaper to reclaim sewage than it is to take the water from the sea and turn it into drinking water. which is why we all need to embrace the whole NEWater thing. So there are 5 desalination plants, the 5th one under construction, and a 6th one is planned somewhere along the north coast in the next couple of years. Oh, I think I've looked at that one. Yeah, sorry, I think I've got some double counting here. Excuse me. Oops. Okay, so then we talk about recycled water. So the main recycled water event in Singapore is called NEWater. I think I'm sure you've all heard of that. It's a high quality, purified water, which is even better than drinking water standards and is produced from used water. Actually, Colin, I think I might ask you to speak about this now. Is that okay? It's more up your street, really.
Okay, yeah, we'll do. Hi, so yeah, so recycled water, as Gerry says, is produced using sewage. Now, in Singapore, there's been it's all about branding and the public, you know, if like bringing the public along as well. And we as if you're in the UK, you call it sewage or wastewater. Here the term is used water because the view is that it's used once, it can be used again. So it is very pure water. It has to be remineralized so that it's less corrosive. So it's purer than normal drinking water. It's got to have some lime and that put back into it so that it's not too corrosive. As Gerry said, most of it is used for indirect. Is used in industry for direct non-potable use, but sometimes it is added back to the reservoirs for indirect potable reuse. And next slide, please, Gerry. So at the moment there are at the moment there are 3 treatment plants. Well, there's 2 at Changi. If I start on the left, yeah. So next to Changi Airport, the large water reclamation plant is there. There are 2 plants on top of the treatment units there, and we have another one that we're designing at the moment, which will be Changi NEWater Factory number 3. At the top of the island, there's Kranji. They're moving downwards. There is Ulu Pandan, sorry. Yep, there's Ulu Pandan. And then on the far left is Tuas, which we'll come on to talk about later. That's in design or in construction at the moment. And next slide. Okay, so there is a separate distribution main for NEWater all the way around the island, and it's called the NEWater Infrastructure Pipeline, or NIP. And you can see there that the Changi NEWater Factory is at one end, at the right-hand side, picks up Bedok, comes around the top of the island. There used to be a plant at Seletar, which has been decommissioned, but Kranji pushes in at the top, and then the bulk users are in the Jurong area, and that's important because that's where the next NEWater plant will be, is in Tuas, and that'll feed into the Jurong Island network, or feed into this network near Jurong Island.
I'm not sure if anyone realized that there was a separate NEWater infrastructure distribution pipeline in Singapore, which has been very forward-thinking of the government.
Mm-hmm. Yeah. As well as industrial use, there is a lot of publicity around NEWater. You can get a bottle of it, usually at National Day parades. Oh, yep. The next slide. So, I'd say it's perfectly safe to drink. I have drunk it. And also there's beer as well. As part of Singapore International Water Week a couple of years ago, they did brew a batch of beer from NEWater.
And we all survived.
Yes. Okay, thanks.
Okay, I'll just jump back in here, can. So I spoke about the need to manage storm water. Now Singapore's got a separate system. So in other words, the rain does not go into the sewers. The rain goes down the canals, for example, the one on Bukatima Road, and makes its way as quickly as possible to the sea. And that's essential, as some of you may recall, the famous flooding events that happened on Orchard Road over the last few years. And that's really because the frequency of storms has increased. What used to be a 1 in 100-year storm is now probably a 1 in 5-year storm, which is a sign of climate change. Now, used water is collected in sewers and ends up in the deep tunnel sewage system, which we'll talk about in a minute. And of course, like I said earlier, rainfall in Singapore is much higher than many other countries, as we can all witness. So here's some examples of the major storm drains in Singapore. Not small things at all. I don't know whether you've noticed or not, but the government is currently, or PB is currently undertaking a series of projects to actually widen these things because they're no longer big enough for the storms. Okay, so what we like to do now is talk about used water and how that has evolved over the years, and it's an essential part of our total water management system. So in the past, there were 6 sewage treatment plants, or water reclamation plants, dotted around Singapore, largely in the same sort of area as the drinking water plants as we showed earlier, but they tended to treat the local catchment, I'll just call it that, the local sewage network. And so this would be the phenomenon here where you collect wastewater from residential and commercial buildings, and then it invariably gets pumped to an end pumping station, which would then feed the treatment plant. And of course, all of that in Singapore takes up a lot of land. And in the early 1990s, PB decided to change tack on this and went for something called the Deep Tunnel Sewerage System, DTSS. So those 6 distributed treatment plants were consolidated and replaced with the deep tunnel sewerage system, and I'll come on to what that looks like. But the concept is that there's no intermediate pumping anymore. Everything from residential and commercial buildings gravitates into the deep tunnel sewer, and then it basically ends up at the influent pumping station to, for example, Changi WRP, and that's the only pumping that there is. Of course, what that means is that the pumping station is very deep. And for example, it's Changi, it's about 70 meters deep by the time it gets there, allowing for gravity. And at our new treatment plant at Tuas, it's about 80 meters deep. So then it gets lifted up for treatment. And in doing so, you can free up the land that was occupied by those other treatment plants, and also all those intermediate pumping stations. Not only that, but it gets rid of the potential for odors in the environment, etc. So it's got a much better environmental footprint. Okay, so DTSS, Deep Tunnel Sewerage System, was conceived in the 1990s, and the idea, as I said, was to consolidate those treatment plants and to connect them using this deep tunnel. And it's been modified a little bit over the years, where the original idea was to have a treatment plant at Changi and another one at Tuas, which is only being built right now. But this third one at Kranji has come into the play right now, so we have sort of a triangle of treatment plants, and each one of those is there because in each area, NEWater is manufactured and used, and is also pumped into the NIP system. Yeah, so at the end of the 1990s, the DTSS phase 1 was finished, and you'll see that on this diagram, which shows the North Tunnel, which runs along the SLE and makes its way down to CTE and across the PIE over to Changi WRP, and it picks up. There's a spur tunnel there, which picks up from Ulupandan, I believe. So that was commissioned back then, and it was always the intention to extend that out to the west, and so that extension is currently underway, and that's called DTSS Phase 2, and it extends the tunnels, and it culminates at the Tuas WRP, which is part of the Tuas Nexus, which we'll talk about in a minute. The tunnels are vary in diameter The main tunnel is about 6 meters diameter, and then it's got a lot of spur tunnels which feed into it. They're called link sewers. And so yeah, it's a very that allows all of the sewage from the various parts of the island to be treated at these 2 treatment plants. And if one treatment plant is not available, some of the sewage can actually be diverted to the other one. So a very ambitious scheme. At the end of the DTSS 2 is the Tuas Nexus with Tuas WRP. I think I'm going to ask Colin to come back in here because he's very much involved in this. Colin, do you want to talk to us about this?
Yep. Okay. So the aim of TWRP, and it's part of a policy to look at, we've talked a lot about water being a critical resource for Singapore, an issue of national security, but also energy as well. There's a lot of energy being imported. And this was to look at those 2 aspects and look at, well, how can we reclaim as much water as well as reclaim as much energy? And it was seen that there was a lot of synergies between those 2 aspects. So this is on the site at Tuas. It was decided to use part of it for water reclamation and then part of it for an integrated waste management facility. So these are they're 2 plants. One is will be operated and owned by PUB. The other is going to be owned and operated by NEA, who have the responsibility for all wastes. So if I just go through some of the processes, so
synergies here, do you want?
Yeah, that's good. So, sorry, can we just go back to the previous slide just a minute? I just wanted to talk about what the overall purpose was. Yeah. So, if you're working from the top right-hand corner, obviously there's a lot of the top middle, from the homes and industries, there's a lot of incineratable waste, household recyclables, and food waste. And at the moment, generally that all goes into one bin outside the house. Well, there's often a recycle bin, but there is a real push going on at the moment for food waste to be separated. You may not have seen it, but there's a lot of there's trials going on in canteens and army camps and schools and wholesale markets to separate food waste. And I think all developers now have to put in 2 rubbish chutes into the new HDBs, new condos. And that is the aim is to separate food waste. So that comes into the IWMF. There's a material recovery facility for separating anything that can be recycled, and anything that can't be, or all the incineratable waste goes through a mass burn incineration process to produce steam. And then that steam is then used to generate electricity, which is then fed back into the grid. All the food waste that comes in gets pre-treated, so just the plastics that get taken out. That then gets pumped across to the water reclamation plant. So that's the first of the synergies, really. And there it's co-digested. So we go down these. Food waste is co-digested in the water reclamation plant with all the sewage sludges, and that produces methane or biogas. And that biogas is then pumped back across to the incinerator, and it's used in their superheater. So they'll be pushing up the steam pressure and temperature, and by that gaining more efficiencies in the steam turbines. The second one is obviously electricity. The TWRP uses quite a lot of electricity, and its sole source is the incinerator. Is the IWMF. Obviously, the IWMF is putting out a lot more energy than the Tuas WRP needs. The third synergy is steam. So they're bleeding off part of their steam, and we're using that at TWRP to break down some of the biomass. Wastewater or used water is treated through a couple of processes. Settlement is one, but the main process is biological, where you're keeping a biomass alive, you're aerating it, and obviously it grows. It consumes pollution, but at the same time it's reproducing, and the excess needs to be treated. If you digest it, you get some good destruction and get biogas. But if you pressure cook it using steam, you can break all the cells apart through lysis, and then you can the destruction in the digesters, which is another an anaerobic biological process, is much greater, and because of that, the biogas produced is much greater. So the aim here is to recover as much of the carbon in the used water and in the food waste as methane, and like I say, that's used to increase the power generation. Obviously, the processes at IWF have leachate, so we do treat those in the water reclamation facility. There's a synergy of manpower, and the admin building is shared. Also, there's screenings that are used, that all the plastic debris that's taken out of used water is taken into the incinerator for burning. Industrial water, all the processed water needed by the incinerator is produced by the water reclamation plant, along with any new water. So they've got two grades of water. That's one thing that maybe hasn't come out yet. The Tuas water reclamation plant separates industrial used water from domestic used water, and NEWater is obviously the one fed back into the NEWater network, but there is a lower grade industrial water which some industries prefer as it's a lower price. One of the biggest used synergies is the sludge, which is coming off of both the settlement and the waste activated waste, the waste biomass. That's after digestion. There's still solids left. That's dewatered to about 28%, and then it's put across to the IWMF, and they have incinerators which will burn the sludge. And again, the heat from that goes to produce more steam and more electricity. And then there's the last synergy is chilled water. There's just a common chilling plant for all the aircon for the site. There is one other which is being looked at and it's been put on hold, and that's the recovery of ammonia. The IWMF need ammonia for their flue gas cleanup, but at the moment that's quite developing technology, and that's been put on hold until the plant's commissioned, and it can be seen how effectively we can strip ammonia out of the used water. This is an overview. So this is the plant. It's been designed in using BIM up to 6D, and we are tendering it in BIM as well. So the tenderers receive a read-only copy of the model, so they can do their own extractions, sections, and they bid on that. And then when the awarded contractor is then given ownership of the model to develop it into the as-built, so that PUB will have if you like, a digital twin of the treatment plant. And it's particularly important here. We have 18 contracts. 8 of them have been let so far, and we're using it monthly. BIM submissions are used to both look at the interfaces physically, and also because it's programmed with a time in, we're looking at time interfaces as well in the construction sequencing.
I'm just going to go to the next slide for a moment. Okay. So
Cool.
let me just jump in here for a minute.
Yeah.
So
it hasn't gone to the next slide yet, Gerry.
Oh,
but it might. It's a big one, I think.
Is it there yet?
There's a video embedded in it, so it might take a bit of time.
I'll come to that. Sorry, the DTSS2 has got 2 tunnels. The west of Singapore is very industrial by comparison with the east. And so there's lots of different companies over at Tuas which produce waste, which is discharged into the public sewage network. And while NEA has got guidelines for what the quality of that should not exceed in terms of the poor quality of it, quite often that is exceeded, I think. And so it ends up at the wastewater treatment plant. And so the issue is that it's very difficult to produce NEWater from such a soup. So what PB's response to that was to divide the catchment over in the west into 2, and to take the highly industrialized parts of it through a separate tunnel to the Tuas WRP, and the more domestic catchment through its own tunnel. And so what happens at this treatment plant is that we have two separate treatment streams, one for the industrial catchment and one for the domestic catchment. And all of the new water is produced from the used water from the domestic catchment, because it's much more predictable in terms of quality. The used water from the industrial catchment will be turned into something called industrial water. I think Colin alluded to it earlier. It's a lesser quality than NEWater, but it's perfectly acceptable for industrial use under some applications. So really, we're applying this fitness for purpose for the final product. Yeah, so as Colin said, we're very excited by this. We'll just give you an idea. There's a video here. Is there, Colin? No. Okay, these are the. This is an example of our influent pumping station. It's very deep and a big hole in the ground. It's 52 meters diameter, each one of these shafts. If you think about that, it's pretty phenomenal. And then the domestic pumping stations are 80 meters deep, and that's to accommodate the gravity flow from the sewage system. And then, of course, it's lifted up to the treatment plant, and so we're through some very large pumps. Colin alluded to the fact we're delivering this plant using the latest BIM, and in fact, we won this award for the Bentley Year in Infrastructure in 2019 for what we just described. So we're very proud of that. So I think we're coming towards the end of our introduction, and so really wrapping up to say what is to come. So more desalination plants, more NEWater plants, major upgrades of Waterworks. I think the CCK Waterworks in the West is the first major application of something called ceramic membranes for the treatment of drinking water, and that combined with ozone and activated carbon is seen as a very robust treatment process. And I think what you're going to see is that all of the other treatment plants will adopt that treatment process, and so that's going to be major reconstruction of all the treatment plants. Co-location of facilities. The Mandai Nexus is the next thing coming up. The Kranji plant that we showed you on our treatment plant, our map of Singapore, the Kranji WRP, is going to be moved to down nearer the zoo, and that'll be a major relocation. And also there will be they'll replicate this Nexus approach. Interestingly enough, though, at that one, they're going to change it from the waste energy water nexus to include food. I think when I say food, what I mean by that is they're going to extract nutrients from the wastewater and use it as a feedstock for growing crops. And that's part of the government's 30 by 30 initiative, which has the ambition of producing 30% of Singapore's daily food consumption locally, and that's no mean feat, I'll tell you. As well as that, there are consumption reduction measures in place. The advanced metering infrastructure project is to put smart meters in all of in everyone's house in Singapore, and to allow you then through your personal handphone or laptop to go and be completely in control of your water consumption. And of course, the idea there is that if you know how much money you're spending, then you'll control it yourself, and you will help reduce the consumption across the island. So the first 300,000 meters are being installed over the next couple of years, and that after that is up and running, then they'll do the rest of the island. Singapore is a hotbed for treatment, the development of new treatment technologies, which is why I said at the beginning it's a very exciting place to be a water engineer. And that will continue, I think. And PB frequently puts out challenges to the global industry to see how they can help them test bed and develop research through research and development, commercialization of technology. And finally, of course, the weather is changing. I think you'll have seen the Prime Minister at National Day a couple of years ago make the statement that they're going to spend $100 billion over the next 20 years or something on increasing the sea defenses and making us ready for the rising sea levels. That will affect the drainage on the island because it ain't going to work anymore. So, yeah, lots of fun to come. That's really the end of our presentation, and we're open for questions.
While we're answering questions, I'll just flick on the. We did have a short video which I'll just put on now. If I could just take over, if that's okay, Gerry.
Sure.
Can you see my slides?
I don't think so.
Hang on, I'll do it again. Is it through now?
I can just see the overview slide of Tuas.
Yeah. Okay. Yeah. No, I was just waiting to that. This was just we give the tenderers a video of the model, and this is just to illustrate really one of Gerry's points, that extremely deep pumping stations. These are the 3 pumping shafts. You can see there they're extended spindle pumps. You can see by the staircases there how deep 80 meters is.
We're currently building this thing. We're digging a hole at the moment. It's a long way from looking like this.
But also the multi-story ventilation rooms above, so it's quite a tall structure in itself, just above the building.
Okay, thank you all for listening.
Well, Gerry, Colin, thank you very much. It was a superb presentation. I think it's got us all excited here. So I think with that, we're going to open up the Q&A and try and get as many interesting questions as we can here.
I hope Colin can answer them.
So maybe going to kick off with, let me find the right place here. Sorry. So the first question is, would it be possible for Singapore to become independent in water? And if so, what steps would be needed?
Well, yeah, so I'll have a go at that, Colin. You can jump in. So the real challenge here is not being independent in water. It's the energy associated with that, because as you can see, the energy consumption of desalination, which is our only sure weapon against, that brings to independence, is very high. And so all we're doing is transferring our problem from the water supply to the energy, and of course the carbon footprint of that is very high. So so what needs to happen there is that desalination technologies need to progress such that energy use is lowered, and that's one of the challenges that PUB has put out to the global community. Interestingly enough, the real way forward in this is something called biomimicry, Colin, right?
Yeah.
Which basically looks at how nature does it with little energy. And so there are some plants and fish that, for whatever reason, are able to desalinate water. And of course, if we can find the holy grail is to find how they do this, and therefore to reduce the energy associated with desalinating water. So that's the real challenge. I
think I just add on that. I think Singapore is on track to have the capacity. It's not the capacity issue; it's also the peaking. We talked about storage of source water, but it's not just the processing capacity. You've got to be able to store enough feedstock to keep supplied, and that's the other big challenge. And that's why desalination has that advantage of having the large storage. I did see one question about could you use the DTSS to store? You can, but it's a very small volume. Even though the tunnels are 3 meters in diameter, it's still relatively small to the flows that come down. To give you an idea, the Tuas plant's capacity is 800 megaliters per day, so that's 8 million liters per day, which I think is about, please don't check this, but it's probably about 8 cubic meters per second. So 8,000 liters a second.
Okay, I think that helps put it in perspective, Colin. That sounds like a huge amount of water, no matter how we think about it, which I'm sure we're wasting daily on many things we shouldn't be wasting it on. Yeah, a slightly different take on that, and I think you answered this partially, but is there a sort of technologies that are being applied there now until we find that chalice with all the secret sauces, how we're going to do it in the future? What new technologies are you starting to see coming in to help reduce the energy demand?
If we just, I did, hopefully this slide comes in. Yeah. So this is just a.
You're talking now about with sewage treatment, right?
Well, I suppose what I'm saying is that, yeah, as Gerry said, there's the efforts to improve technology to reduce the demand for RO, but for water treatment. But there's the other side is how can you capture the energy that's already in used water? There's quite a lot of embedded energy in waste. Both, we talked about municipal waste where it's a mass burn, but there's a lot of energy or carbon in the used water, and the treatment processes we've been looking at the aim is to try and capture as much carbon as possible. If you look at the domestic flow stream at the top left, first of all, you settle out as much of the solids as you can, and here what we're doing, we're actually enhancing that by adding some bacteria in. Naturally occurring bacteria, and what they do is they just rapidly absorb the carbon, and then that carbon, as it then settles, is then pushed into the digestion processes to produce more methane. But the other thing is that in a traditional plant, the second stage where it says membrane bioreactors, this is there just to oxidize the carbon, the ammonia to nitrates. If you can take it out early, then obviously you save energy. You don't need to aerate the waste further down. So the aim is both to maximize the amount of energy you can recover and also reduce the amount being needed for treatment. The other side, just going down the flow stream, the membranes at the back end of the bioreactors, one of the big technological changes has been, if you like, to merge what would have been the wastewater treatment plant with the water reuse plant. In the past, you'd always come out as an effluent. You then go through either microfiltration or ultrafiltration membranes, and then into RO. But what we've done here is we're using membranes in the main wastewater treatment process to avoid the whole process unit of a MF or UF membrane plant, which again saves energy. You don't have to pump it through membranes. So I think there's a lot of, we talked about thermohydrolysis to try and recover more energy from the carbon. So there is a real push on to try and see how much you can generate. And according to our calculations for the design, up until the membrane filtrate, the plant's energy neutral. It produces as much energy as you need to as is needed to treat. At the moment, we haven't got the RO and UV in that mix, but up until what is a very pure water, it is energy neutral.
So from a mechanical perspective, the two big energy users on any wastewater treatment plant is pumping and aeration to keep the bugs alive. And the more air you have to produce to do that, then of course the more energy you use. So the focus of most wastewater treatment technologists is to try and reduce those both. So there are special bugs now. We've developed them over the years that can help reduce the aeration demand dramatically, and they are starting to be put into practice at large scale, and we have designed this plant to allow that to happen as it takes a while to embed itself after the treatment plant is started.
Yep.
Excellent. Well, it's certainly exciting to see you're trying to deal with two of the biggest problems that the world seems to face, which is water, and at the same time the carbon, how we manage the carbon coming off the energy that we're consuming. There was a question here further down about in whether the plant had some CCS capabilities as well.
Yeah, not as such. Only what I've described there is that we're trying to pull as much carbon into the anaerobic digestion to produce methane.
Right.
And that methane is then obviously burned to carbon dioxide in the superheaters. I know PUB are looking at alternatives use for that methane. Could it be used for hydrogen production or green methane? You know, they're all ways and means to look at alternative uses to reduce.
Yeah. So one of the problems that we also have here in Singapore is that the commercial models which might apply in other parts of the world for the use or the beneficial use of such things doesn't really exist here. We've got nowhere to put the sludge on the land. We haven't got any users of the some of the things that we could recover. They might be able to be used in other countries nearby, but there's no real use for them here on the island, and that really is something that makes the government take steps that might not be taken in other parts of the world. Most of the engineering we do on these water treatment plants and wastewater treatments is about security of supply, security of performance, because if this wastewater treatment plant fails, there's nowhere else for the sewage to go. You can turn a drinking water plant off as long as you've got another one, but you can't turn a sewage treatment plant off. It has to be there all the time, right? And so that really is a challenge for us. Now, I'm quite sure you're aware that on another subject that there are 32 permitting agencies in Singapore, and everything that we build has to go through all 32 of them. One of the most recent ones, which has affected us quite dramatically, is the remit of the Ministry of Home Affairs, IMechE, and they classify drinking water plants and any plant that produces NEWater as a key installation, which needs to operate during times of national emergency. And so they set us nice little exam papers in that they invent terrorism scenarios that we have to demonstrate that our treatment plant is designed to survive in whatever way we say it should survive, whether it's only half the plant or whatever. So that really affects how we lay out our treatment plants. And it also makes some of the people that apply technologies around the world that they say, well, why don't you use ours? You can build a smaller this or a smaller that. And say, we don't care. We need to comply with the government agencies, and we need to look 100 years in the future. And by the way, we might not always want your piece of kit. We want somebody else's piece of kit, right? So it's quite different dynamics when you take water security as an existential issue and how it affects your engineering.
Well, these are great examples for us all of the different impacts and different requirements that can impact your design as you're looking forward into and many things that you would not necessarily think of when you start off down a path of looking for the best technological solution. There's many impacts into that at the same time. So it's a super example of that. Thank you very much. I'm going to cut short, if I can, the
Sure.
Q&A here, I think, because we're running a bit behind schedule. I'd first of all like to thank both of you on behalf of the Singapore branch of the Institute of Mechanical Engineers. Superb presentation, definitely eye-opening, and I think it helps deepen our understanding of really what is involved in keeping the precious liquid flowing from our taps.
Thank you.
Yeah, I think we can say this has certainly whetted our appetites for more to come in the series, and I'm personally looking forward to those sessions more than ever.
We'll bring some people who actually know what they're talking about next time.
Thank you very much. Well, no, you certainly knew your stuff, so we appreciate that very much. And with that, I'd like to invite Koji Oberoi, our Singapore branch chair, to say a few words and invite your feedback on in general. So, Koji, if you can turn on your mic and we can